There's something about the way nights get quiet that makes it easier to think about things that don't have answers. Not the noisy kind of quiet, the kind with distant traffic and the occasional creak of a house settling, but the deeper kind, where your thoughts start to slow down and the stuff you normally rush past starts to have a little more room. That's a good place to be tonight. That kind of slowness is, in a way, what this space, the sleepy physicist, has always been for. So if you're here, already tucked in, already drifting a little, thank you for being here. Genuinely. This keeps going because people keep listening, and that's not something to say quickly and move past. Tonight is about a galaxy, which, right, that's a broad thing to say, but this one is specific. This one is strange in a way that doesn't resolve into comfort the more you look at it. Let's start with the photograph, because that's actually where the whole thing begins. It was 1950. An astronomer named Art Hoag was doing the kind of work that feels more like cataloguing than discovering, sorting through photographic plates of galaxies, most of them following predictable shapes, spirals and ellipticals and the occasional fuzzy irregular. The plates were glass, actually, big, fragile, coated in a thin layer of photosensitive emulsion. You'd hold them up to light, squint through them, record what you found. The room would smell of developing chemicals and whatever dust had settled since the last time someone cleaned. Ordinary work, the kind that fills most of science, which is mostly patience and repetition and the occasional thing that stops you mid-thought. And something stopped him, not in a dramatic way, more the way you notice something slightly off in a room you've walked through 100 times, a door left open that's usually closed, a chair at a wrong angle. The galaxy in plate after plate had a particular logic to its shape, a centripetal pull toward the middle where mass gathered and light concentrated. This one didn't. This one had a core, and then a gap, and then a ring of light surrounding the whole thing like it had been arranged, placed, which is not obviously what happened. But the word that comes to mind looking at it is arranged, and that word doesn't quite leave. Hoag published a short paper. He noted the shape, called it peculiar, which in scientific classification means something more precise than it sounds. Peculiar means this does not map onto existing categories, but we do not yet have enough information to build a new one. File it, note it, come back later. The later came slowly. Photographs improve, telescopes improve. What looked like a smear in 1950 gradually resolved, decade by decade, into something more detailed, more textured, more strange. By the time deep imaging technology existed to look at Hoag's object, which is what it came to be called, Hoag's object, a name that manages to sound both clinical and slightly personal, the strangeness had not resolved into sense. It had sharpened into something more defined, which made it more difficult, not less. Here is what you see when you look at it clearly. A tight, bright core of yellowish light at the centre, dense and settled, the colour of stars that have been burning long enough to have earned a kind of stillness. And surrounding that core, separated from it by a gap, an actual measurable gap, not a trick of contrast, a ring, a nearly complete ring of blue-white light, younger stars still forming in some places, arranged in a circle around the outside as though drawn with a compass and then left there. Between the core and the ring, almost nothing, just the quiet, just the dark. The shape is not quite like anything else that appears regularly in deep sky surveys. There are other ring galaxies, a small number, a strange fraction of the galaxies we've catalogued. But Hoag's object has a completeness to it, a near-perfect circularity that makes it look less like the result of physics and more like the result of intention, which of course it isn't. But the eye keeps going back to that idea, and the eye is not entirely wrong to notice something worth questioning. What makes a shape feel wrong is usually not the shape itself. It's the mismatch between the shape and the process that should have produced it. Galaxies have shapes because of physics, the way gravity behaves at scale, the way clouds of gas collapse and rotate, the way interactions between galaxies over billions of years leave particular signatures in the structure of what remains. Spirals form because matter rotating under gravity naturally settles into spiral patterns given enough time and the right initial conditions. Ellipticals form when galaxies collide and their orbiting stars are scrambled into randomized paths that average out into a smooth, featureless egg shape. Every shape is a record of a process. So when a shape appears that doesn't match a known process, or matches several processes partially, imperfectly, without fully committing to any of them, it stays open. The file doesn't close. The photograph gets pulled out again. Hoag's object has been that photograph for over 70 years now. And the thing is, it doesn't feel broken. It doesn't look like something went wrong. It looks actually like something went very precisely in a direction physics doesn't often go, and then stayed there, stable, patient, slowly rotating 600 million light-years away from anyone asking questions about it. There is something almost unsettling about a mystery that isn't dramatic. Not a cataclysm, not a collision frozen mid-violence, just a shape holding its shape waiting. The gap between the core and the ring is where that feeling lives most clearly. That gap has a quality to it that data can describe but not fully account for. And what's inside that gap, or rather what almost isn't, that's where things start to get interesting. The light from the core and the light from the ring are not the same age, not even close, and what that means, quietly, for what this object is and was, that's something to sit with for a little while. 1950 is not that long ago, not in the way people usually mean when they say something isn't long ago, not long ago like a grandparent's memory or a war still felt in the architecture of a city, but in the context of astronomy, in the context of how long humans have been pointing instruments at the sky with any real precision, 1950 is almost recent. Modern telescope technology had only been developing seriously for a few decades. The photographic plate, that heavy, fragile, chemical-coated glass, was still the primary way astronomers recorded what they saw. Digital imaging didn't exist. Computer processing didn't exist. What existed was patience, darkrooms, and the slow accumulation of glass plates stacked carefully in wooden drawers. Art Hoag worked at that edge. He was a quiet figure in the literature, not a household name, not the kind of astronomer who appears in popular histories with dramatic anecdotes attached. He published carefully, he classified, he did the work that most of science is actually made of, which is not revelation but accumulation. The building up of a body of observation detailed enough that eventually something in it starts to resist easy explanation. The galaxy that would carry his name was not what he was looking for. That's worth staying with for a moment. He wasn't looking for it. He was classifying, sorting through plates of galaxies captured during survey work, applying the categories available to him, moving through a checklist that had a logic and an endpoint. Spiral, elliptical, irregular. The categories were Hubble's mostly. Edwin Hubble had constructed a classification scheme in the 1930s, a simple tuning fork diagram, ellipticals branching into spirals with and without bars, and for decades that scheme held. Most galaxies fit. Most galaxies cooperated. This one didn't cooperate. Hoag wrote his paper in 1950. It was short, a few pages, careful language, a description of the object's morphology, and a handful of tentative explanations, none of which he pressed with any force. He noted the bright central nucleus, he noted the outer ring, he noted the gap between them, and then he said, essentially, This is unusual, and here are some things it might be, and I am not certain, and someone should look more carefully. Someone eventually did. Several someones, across several decades with progressively better instruments, and each time the object gave up a little more detail and retained, somehow, the same essential strangeness. The ring stayed a ring, the gap stayed a gap. The core stayed old and yellow, while the ring stayed young and blue. The mystery didn't dissolve with better data. It focused. There's a particular quality to a scientific problem that sharpens rather than fades under closer inspection. Most mysteries in astronomy turn out to be resolution problems. The image improves, the ambiguity collapses, the explanation arrives. The object turns out to be two overlapping galaxies seen from a particular angle, or a trick of the photographic emulsion, or something already catalogued under a different name. The file closes. Hoag's object kept its file open, and it did something slightly more difficult than simply resisting explanation. It collected explanations without fully accepting any of them. Theories arrived, each one reasonable, each one carrying enough internal logic to feel almost convincing, each one leaving something unexplained at its edges. The object became a kind of test case, a thing to think with, a shape that accumulated hypotheses the way certain problems accumulate footnotes, not because the core question was unanswerable exactly, but because the evidence needed to close it was either too old to find or had never been the kind that leaves a detectable signature. This is incidentally a frustrating thing about deep time. Physics is not shy about what it does. Every process leaves traces, but traces degrade, signals weaken. The further back you try to read, the more the record thins out into something that can support multiple readings at once, and you're left holding a photograph of an outcome without the footage of how it got there. Hoag had the photograph. He died in 1993. By then the object had been studied in multiple wavelengths, modelled in early computer simulations, included in catalogues of peculiar galaxies alongside other objects that refused to behave. His name had settled permanently into astronomical literature in the way names sometimes do, not as tribute so much as habit, the way a street name outlasts the person it honoured. Hoag's object, peculiar galaxy, right ascension 15 hours, 17 minutes, declination plus 21 degrees. The coordinates make it sound findable, and it is findable, with the right equipment in the right part of the sky on a clear night. In the constellation Serpens, which is one of those constellations that sounds more dramatic than it looks, a faint scattering of stars with no particularly obvious shape. Somewhere in that direction, 600 million light-years out, the object sits, rotating, building new stars in its ring while its core quietly does nothing in particular, which is what old stellar populations do. They persist. They cool incrementally. They radiate the light of processes long completed. The light reaching us left before the first vertebrates appeared on Earth. That's not a metaphor, it's just the arithmetic of distance. 600 million years ago, something in that galaxy emitted the photons that will, tonight, be somewhere between there and here, still moving. There's a strange intimacy in that, maybe. Or, no, intimacy isn't quite the right word. It's more like correspondence. A letter sent before the sender knew there would be anyone to receive it. Arriving now, containing information that was accurate when it was written, but describes a place that has since changed in ways we cannot know. Hoag classified it, filed it, moved on to the next plate. The object kept being strange without him. It didn't require his attention to remain itself, and 70-odd years later, the file is still open, the theories are still partial, and the shape is still, somehow, arranged in a way that resists the easy word for what made it. The core is old, the ring is young, These two facts sit side by side inside the same object, and they don't quite explain each other. What the difference in their ages might mean and how to read a gap that separates them takes a little longer to unpack. Rings don't just appear. That sounds obvious when you say it out loud, but it's the kind of obvious that's worth sitting with for a moment, because the shape itself, that clean, closed curve, equidistant from a centre, feels almost too resolved, too finished, to be the product of the same chaotic gravitational machinery that produces everything else in the universe. Spiral arms are messy at their edges. Elliptical galaxies blur softly into the surrounding dark. Even the most regular structures in nature carry the texture of the process that made them. Rings feel different. Rings feel, decided. And that feeling is worth questioning because physics doesn't decide anything. It just proceeds. So what actually produces a ring? Start with something smaller. Saturn's rings are the version most people carry somewhere in their memory. That flat, bright disk of material caught in orbit around a planet, visible through even a modest telescope. One of those sights that tends to make people go quiet for a moment when they see it for the first time. The rings are made of ice and rock, ranging from grains the size of sand to chunks the size of a house, all of it orbiting Saturn at different speeds depending on distance, all of it held in that thin, flat plane by gravity and by something called the Roche limit, the boundary inside which a moon cannot hold itself together against the tidal forces of the planet it orbits. Material that crosses that boundary gets pulled apart rather than coalescing. It spreads, it flattens, it becomes a ring. Saturn's rings are debris that didn't become something else, or became something else and then got dismantled. The exact origin is still, actually, debated, whether it was a moon that drifted too close, or material left over from the solar system's formation that never quite gathered into anything larger. The answer isn't settled. But the process is understood. Material at the right distance, under the right gravitational conditions, will prefer a ring over any other configuration. The ring is the stable solution, not chosen, just arrived at. Now stretch that idea. A smoke ring, which is the different thing entirely physically, but to bear with this for a second, forms when air moves through a circular opening, and the fluid dynamics of the air cause the edges to curl back on themselves, forming a rotating vortex that holds its shape as it travels. The ring isn't held by gravity, it's held by the momentum of its own rotation, the inner structure of the flow reinforcing itself as it moves. It's temporary, obviously. A smoke ring disperses, but while it lasts, it has that same quality, that self-contained, closed-curve completeness that the eye registers as almost deliberate. These are the only two examples worth holding, and the second one I'm not entirely sure belongs here. It's a different kind of ring, a fluid dynamics ring, and the mechanism has nothing to do with what happens at galactic scales. But the quality of self-reinforcement, the idea that a ring can be a stable solution rather than a transient accident, that part carries over, just with different physics underneath. At galactic scales, a ring of stars forms when something forces material into circular orbits around a center. The forcing can come from several directions. A collision between galaxies, at the right angle and speed, can send a shockwave outward through the disk of one of them, compressing gas as it passes, triggering star formation in a ring pattern that expands outward from the point of impact like the rings on the surface of water when something falls into it. This is called a collisional ring galaxy, and it's the most common explanation for ring structures when they appear in deep sky surveys. The Cartwheel Galaxy is the most photographed example, a large spiral that another galaxy passed through nearly perpendicularly. the impact sending a wave of star formation rolling outward, leaving a bright ring of new stars at its leading edge. The rings in these cases are not permanent. They are moments in a process, frozen, more or less, by the timescales involved. The ring expands. The star formation it triggered produces massive blue-hot stars that burn brightly and briefly. The wave moves on. What's left behind after the most massive stars have already lived and died is a ring that dims and ages, the stellar population cooling and reddening as millions of years accumulate. Hoag's object has a ring of blue stars, young, still forming, still burning with the particular intensity of early stellar life. This ring has been stable, structurally stable, not just a passing wave, for long enough that its shape is complete and its gap is clear. That combination is the thing that doesn't resolve easily. A collisional ring should be expanding, transient, the edges of the wave already dispersing by the time the ring looks this clean. A ring this complete, this circular, this apparently stable, implies a different kind of process. Or possibly the same process viewed at a very particular moment, or possibly something else entirely that the available models haven't fully captured. The gap is part of this. The gap between the core and the ring isn't just empty space left behind by a receding wave, it's maintained. Something about the structure of the galaxy, the distribution of mass, both visible and dark, is keeping that space clear, while simultaneously allowing star formation to persist in the ring outside it. This is, and I want to be careful here, because it's easy to overstate, this is not obviously accepted from standard galaxy dynamics. It's not impossible, it's not even unprecedented in rough terms, but it is unusual in a way that the available physics describes only partially. A ring at its simplest is a stable solution to a gravitational problem. Material that cannot go inward and will not drift outward finds a middle distance and stays there, orbiting, accumulating, sometimes igniting into star formation if the density climbs high enough. The ring of Hoag's object is made of stars that found that distance, or were pushed there, and have been circling it, some of them still forming for longer than the Earth has existed. What the ring is not is decorative. That's the thing that takes a moment to fully land. The blue light coming from it isn't incidental. It's a record of physics, of gas compressed to the point of ignition, of nuclear furnaces switching on inside clouds of hydrogen and helium, of gravity winning a local argument with pressure and producing, as a consequence, light. All that blue-white light is just fusion happening at a distance. Millions of stars in the process of being stars, arranged in a circle radiating the ordinary product of their ordinary nuclear reactions outward in every direction, including eventually here. The ring is not an aesthetic feature of Hoag's object. The ring is Hoag's object asking a question in the only language it has. The core is not asking the same question. The core is quiet, yellow, settled. And the difference between those two things, the ring's ongoing restlessness and the core's long stillness, is something you can see in the colour alone, if you know what the colours mean, which is where this goes next. Two populations of stars sharing one galaxy, separated by a gap, radiating light of completely different ages. The colours aren't decoration. They're a kind of record, and reading them means thinking about what light carries besides brightness. Colour in astronomy is not aesthetic. It took me an embarrassingly long time to fully absorb that, to stop experiencing the colours in deep space photographs as something added, enhanced, chosen for visual effect, and start understanding them as data. Raw, unambiguous, chemically and physically determined data. The colour of a star is not its personality, it's its temperature. And temperature in a star is inseparable from age. from mass, from the particular stage of nuclear burning it happens to be in at the moment its light left it. Blue means hot. Hot means young, or at least massive, because the most massive stars burn their fuel at a rate so extravagant that they exhaust themselves in millions of years rather than billions, living short and intensely luminous lives before collapsing or exploding. Blue-white light is the signature of that intensity. It's the colour of something spending itself. Yellow means something different. Yellow, the warm, settled glow of a star like the sun, means middle age at best, or the collected light of a population of stars that have been burning long enough to shed their blue-white youth and settle into a slower metabolism. An elliptical galaxy dominated by old stars glows yellow-orange, not because the stars are dying necessarily, but because the ones that burned blue-white are already gone. What remains are the survivors, the smaller, cooler, more patient stars that will outlast their brighter siblings by billions of years, radiating warmly and without urgency into the surrounding dark. When you look at Hoag's object, you are seeing both things at once. The core glows yellow. The ring burns blue-white. Same galaxy, same gravitational system. Two completely different stellar populations separated by that gap, each one radiating the light of a different era. This is strange, not strange in the way an unexplained noise is strange, unsettling, demanding immediate resolution. Strange in the quieter way, the way a fact can be strange when you hold it still long enough to feel the full weight of what it's actually saying. The yellow light from the core and the blue light from the ring are not just different colours, they are different times. The stars producing them have different histories, different ages, different relationships to the gas and dust from which they formed. And they are orbiting slowly, silently around the same centre. Stellar populations have a formal classification in astronomy. Population 1 stars are younger, richer in elements heavier than hydrogen and helium, metals in the astronomical sense of the word, which means anything on the periodic table beyond helium, which is a definition that takes some getting used to. Population 2 stars are older, formed earlier in the universe's history, when heavy elements were scarcer, their composition reflecting a galaxy that hadn't yet processed enough stellar generations to enrich its gas significantly. The distinction maps roughly onto location. In the Milky Way, population 1 stars tend to live in the disk and spiral arms, where star formation is ongoing. Population 2 stars cluster in the bulge and the halo, old enough to predate the disk's current structure. Hoag's object seems to have both populations spatially separated, the core carrying its old stars, the ring carrying its young ones, the gap between them clean enough to feel deliberate, even though nothing about this was deliberate. It just happened. Over billions of years, under conditions that aren't fully understood, the galaxy sorted itself, or was sorted by some event, into this arrangement. The sorting is what resists easy explanation. Here is a thing worth considering slowly. The blue stars in the ring are not just young, they are young in a way that implies active star formation is either ongoing or ended recently enough that the most massive stars haven't yet burned out. Massive blue stars have lifetimes measured in millions of years, not billions. The universe is approximately 13.8 billion years old. The solar system is roughly 4.6 billion years old. Against those numbers, a few million years is almost nothing, a rounding error, a breath. So the star formation in the ring of Hoag's object by cosmic standards is practically happening now, or it was happening when the light left. 600 million years ago those stars were new, or still forming. What they are now, whether the ring has aged, whether the star formation has continued or paused or ended, is information we do not have and cannot get. The light carrying that information has not arrived yet. It's 600 million light years away. The news takes time. There's a version of this that's easy to gloss over. The delay between event and observation feels like a technicality, a footnote, something to acknowledge and then set aside in favour of the more interesting physics. But I'm not sure it's a footnote. The delay is the physics, in a way. The fact that we are seeing the ring's blue stars in what is, for them, early life, while simultaneously knowing that 600 million years have since elapsed, that those stars have been aging in our absence, that the ring may look completely different by now. This is not a limitation of our instruments. It is the structure of the universe. Distance is time. Every observation of a distant object is an observation of a past state. Hoag's object as it exists tonight, in whatever form it has taken across 600 million years of continued evolution, is inaccessible. Not temporarily, permanently. The present tense version of that galaxy is causally disconnected from us. What we have is the 1950 photograph of a photograph taken 600 million years ago. And yet, the light is real, the colours are real, the yellow of the core and the blue of the ring are not artefacts, they are genuine spectral signatures of genuine stellar populations doing genuine physics at a genuine distance. The gap is real, the structure is real. What the colours tell us about the history of that galaxy is a real inference drawn from real data. It's just that the data is old, older in fact than the earliest complex life on this planet. The light from the ring left when Earth had bacteria and little else. Nothing yet with a backbone, nothing yet that would recognise warmth or cold or the pull of gravity in the way bodies eventually learn to recognise it. The light has been travelling since before there were eyes, and it carries encoded in its wavelength the temperature of stars it left behind, stars that are almost certainly no longer the same age they were when it departed. The colour tells the truth about a moment that no longer exists. Yellow core, blue ring, a gap of near darkness between them. 3 facts sitting side by side, each one clear in isolation, each one generating a different question when placed next to the others. The age difference between the two populations is not a small discrepancy to be smoothed over. It's measured in billions of years, a span of time long enough for entire galaxies to form, evolve, and begin dying. Whatever produced the ring did so long after the core had already settled into its quiet yellow age. The ring is not a remnant of the galaxy's formation. It is, in some sense, an addition, something that happened to an already old structure. What kind of something? That's the part that stays open. The gap doesn't explain itself. It just sits there between the old light and the new light, dark and clear and oddly patient, as if it's been waiting to us, which it hasn't. Gaps don't wait. As if it has simply persisted long enough for us to notice it and find it, in some quiet way, difficult to look away from. A gap that persists isn't just empty space. It has a shape, a boundary, a stability that implies something is maintaining it, or that the conditions which created it haven't yet relaxed. What lives in that absence physically, and why it stays absent, takes a little time to approach. Here's the thing about empty space, it isn't empty. That sounds like a setup to a lecture on quantum vacuum fluctuations, which I'm not going there right now, that's a different night entirely. What I mean is simpler and, honestly, more interesting in the context of Hoag's object specifically. When astronomers look at the region between the core and the ring, that dark band maybe 30,000 light-years across, separating old yellow stars from young blue ones, what they're measuring is an absence. They are measuring a deficit. A place where density dropped below the threshold required for star formation and stayed there. Stayed there for a long time, long enough for the ring to fully form, burn blue-white, and still be burning. That's not nothing doing nothing. That's something. A configuration of mass and gravity and gas dynamics actively producing a quiet outcome. 30,000 light years. The number keeps coming up in my notes on this, and I keep writing it down without fully letting it land. The Milky Way's disk is roughly 100,000 light years across, so 30,000 is not a negligible slice of what a galaxy can be. It's not a thin boundary line, it's a region, a substantial one, and inside that region, the density of stars is low enough that the gap reads, in photographs, as dark, not perfectly dark, not a true void, just thin. Sparse in the way a high desert is sparse, where you can stand and see for miles and there are things out there, just not many of them, and the space between them is doing most of the work of defining the place. I'm not sure that analogy helps. It might actually obscure the scale, forget the desert. The gap is a region of a galaxy where the expected accumulation of matter didn't happen, or happened and then cleared, or was prevented from happening by the same event, whatever it was, that produced the ring outside it. Those three possibilities are not equivalent. They imply completely different histories, and distinguishing between them from here, 600 million light years away, with instruments that collect photons and infer everything else, it's genuinely hard. Not hard like a complicated calculation, hard like trying to work out what happened in a room from a single photograph taken through a window. Gaps in astrophysical structures tend to form in a few ways. The most intuitive is clearing. Material that was present gets pushed outward by some mechanism, leaving a depopulated region behind. In protoplanetary disks, young planets do exactly this. They orbit through the disk of gas and dust surrounding a forming star, sweeping their orbital path clear, creating gaps that can actually be imaged now with telescopes like ALMA. The planet's gravity pulls material into its orbit or flings it inward or outward, and the gap is what's left. Tidy, mechanistic, one object, one cleared path. At galactic scales, the same basic logic applies, but the objects doing the clearing are less discrete. The timescales are oceanic, and the evidence for what did the clearing dissolves long before we get to look. A ring galaxy formed by a galactic collision, another galaxy passing through the disk perpendicularly like a stone dropped through a drum skin, produces an outward-moving density wave that compresses gas into star formation at its leading edge, while leaving a depopulated region behind it, between the expanding wave and the original nucleus. The gap in that scenario is a wake, the memory of a wave's passage. Hoag's object may have a gap like that. The timing, though, the age of the stars in the ring, the apparent stability of the structure, the near-perfect circularity, these things sit awkwardly against a simple collision model. A collision-driven density wave should expand and disperse. The ring should, over time, lose its coherence. Instead, it persists, circular and clean, and the gap persists with it. There's a paper, I want to say it's from the early 2000s, but I'd have to check, I might be off by a decade, where a group of researchers ran n-body simulations specifically trying to reproduce Hoag's object's morphology. They tested several formation scenarios, including the polar ring model and the Bain instability model, and a couple of merger variations. What they found roughly was that each model could reproduce some features and failed on others. The circularity was hard to get right. The gap width was hard to get right. Getting both simultaneously in a single model without introducing conditions that seemed contrived, that was the problem. Not impossible, maybe, just resistant. The gap specifically kept misbehaving in the simulations. Either it was too narrow or it closed too quickly, or the ring associated with it wasn't circular enough. There's something about the combination of a clean gap and a near-perfect ring that the models strain toward without quite reaching. I find this more interesting than a solved problem, honestly. A galaxy that simulations can approximate but not fully reproduce is a galaxy that's telling you something about the limits of the model, not just the limits of the data. So what maintains the gap now? Whatever cleared it, collision, bar instability, some merger geometry, but happened a long time ago. The event is over. The galaxy has had billions of years to redistribute its material for gas to flow inward, for the gap to fill. And it hasn't filled. The gap is still there, still dark, still roughly the width it appears to need to be for the ring to exist where it exists. This is where dark matter enters quietly without announcement. The visible matter in a galaxy, stars, gas, dust, is embedded in a much larger, much more massive halo of dark matter that doesn't emit or absorb light but does exert gravity. The shape of that halo determines a lot about how the visible matter behaves. In most galaxies, the dark matter halo is roughly spherical and smoothly distributed, and its influence is felt mainly in the rotation curves of the disk. Stars at the edges of a galaxy orbit faster than they should if only visible matter were present, and the dark matter halo accounts for the discrepancy. For Hoag's object, the dark matter distribution has to be doing something specific to allow the ring to persist where it persists and the gap to remain where it remains. A halo with certain symmetry properties, spherical in particular ways, distributed in particular radial profiles, could in principle sustain this configuration. Whether that's what's actually happening is not confirmed. The dark matter halo of Hoag's object has not been directly modelled with enough constraint to say much with confidence, which means the gap's persistence is explained by something we can't see, behaving in ways we can only infer, in a galaxy too far away to probe in the detail we'd need. The gap stays dark. The ring stays bright. And the reason one stays dark while the other stays bright is, at some level, still being worked out. There is one more thing about the gap. In deep images of Hoag's object, the kind taken with extended exposure times, pulling in faint light that shorter observations miss, there are hints of very faint material in the gap region. Not stars exactly, diffuse light, possibly from a sparse stellar population, possibly from scattered light off dust or gas. It's faint enough that characterizing it is difficult. It might be nothing, an artifact of the imaging process, a background contamination. It might be the last trace of material in the process of clearing or the first hint of material beginning to drift back in. Or it might just be what 30,000 light-years of sparse galactic real estate looks like when you expose long enough to see the faint stuff. The gap is not perfectly clean, it's just mostly clean. And mostly, at galactic scales, is about as clean as things get. Outside the gap, the ring keeps building stars, or was building them 600 million years ago, which is the only version of the ring we have access to. What the ring actually is, structurally, and how it holds itself in that near-perfect circle without the kind of support structure most galaxies use, that's a different problem, and it doesn't simplify when you look closely. The collision model is the most intuitive. Another galaxy passes through, perpendicularly roughly like threading a needle at speed, and the shockwave from the impact rolls outward through the disk of the target galaxy, compressing gas as it goes, triggering star formation at its leading edge. The ring is the wave's signature. The gap behind it is the wake. It's clean, it has precedent. The Cartwheel galaxy formed this way, and its ring structure, while messier than Hoag's, follows the same basic logic. So the collision model arrives first in most papers on Hoag's object, gets laid out carefully, and then runs into trouble. The trouble is evidence. A collision leaves marks. Tidal streams, disturbed kinematics, A companion galaxy somewhere in the vicinity still decelerating from the impact or already departed but traceable by the gravitational distortion it left behind. Hoag's object has none of these. No obvious companion, no tidal debris, no kinematic signature pointing clearly toward a recent high-velocity interaction. The galaxy sits alone, its ring nearly circular, its structure undisturbed in the ways a collision should disturb things. Absence of evidence isn't the same as evidence of absence. The companion could have escaped the field of view. The debris could have dispersed over billions of years into something too faint to detect. Maybe. The collision model doesn't collapse under this. It just becomes less satisfying. The bar instability model is less intuitive but worth understanding. Some galaxies develop a bar, a linear concentration of stars running through the nucleus, and that bar can, under the right conditions, funnel material outward to a resonance radius, a distance from the center, where the orbital dynamics allow material to pile up rather than continue moving. A ring forms at that radius, not from a collision, from internal redistribution. Hoag's object shows no obvious bar. The core is round, compact, symmetric. If a bar drove the ring formation, it may have dissolved after doing its work, and bars are not necessarily permanent structures. A dissolved bar is hard to detect, so the model is possible. It's just working with a mechanism that, if it operated here, erased most of its own evidence. That's an uncomfortable position for a theory. Not wrong exactly, just unfalsifiable in the ways that matter. The merger model, a smaller satellite galaxy absorbed by Hoag's object, its material and the disturbance of its infall triggering ring formation, is probably the most discussed in recent literature. Mergers happen. Minor mergers, where a dwarf galaxy falls into a larger one, are common events in galactic history. The infalling galaxy disturbs the disk, can excite density waves, can deposit material at particular radii depending on the geometry and mass ratio of the interaction. The timing, though, for the ring to look this young, blue stars still forming, the population clearly not yet aged. The triggering event can't be too ancient. But a merger ancient enough to have fully concluded, with no visible remnant and no obvious disturbed kinematics, would also be old enough that the star formation it triggered should have moved further along. The blue stars shouldn't still be this blue if the event was long enough ago to be completely invisible, unless the merger was very specific in its geometry, unless the mass ratio was just right, unless. And here is where the model starts to accumulate its own epicycles, particular set of conditions aligned to produce this particular outcome. Each theory has that quality, a workable core, a set of conditions attached to the core that are possible but unverified, a residue of unexplained features that the theory addresses by adding complexity rather than reducing it. There's a version of this situation in physics that's frustrating in a specific way, not the frustration of a wrong answer, which at least closes a door. The frustration of several answers that are each partly right, each explaining different features of the same object, none of them explaining all of it. You end up holding three partial solutions and wondering whether the real answer is a combination. Some collision-merger hybrid, some sequence of events that borrowed from multiple mechanisms, or whether the real answer is something not yet proposed, waiting in a simulation someone hasn't run yet. Hoag's object is probably not the result of a single clean event. Galaxies rarely are, but the specific combination that produced this specific structure, that gap, that ring, that particular color difference, that isolation, hasn't been reconstructed convincingly. The theories account for the shape in outline. The details resist. Whatever happened, it happened a long time ago, and the galaxy has had billions of years to settle into what it currently is. The question of whether that settling is stable, whether the ring will persist, whether the gap will hold, is separate from the question of origin, and in some ways more tractable. The physics of what keeps Hoag's object the way it is might be more accessible than the physics of how it got there. There is a detail in the deep images of Hoag's object that almost nobody leads with. It appears in the gap, that dark region between the core and the ring, and it is not part of Hoag's object at all. In the background, visible through the gap, there is another ring galaxy, a different one, much further away. Caught by chance in the same field of view, aligned by coincidence so that it sits inside the gap of Hoag's object like something placed there deliberately, which it wasn't. Two ring galaxies, one behind the other, separated by an enormous and uncalculated distance, appearing in the same image because the gap in the closer one was empty enough to see through. Astronomers noted this. Papers mention it, usually briefly, usually in a section dealing with the broader image field rather than the object itself. It doesn't change anything about Hoag's object. It doesn't illuminate the formation mechanism or resolve the question of the gap's persistence. It's just there, a background object, an unrelated galaxy, caught in a specific piece of sky at a specific moment of observational history. The probability of this alignment isn't calculated in any paper I've found. Maybe it's not especially low. Ring galaxies exist in numbers, the size deep. Chance alignments happen across deep field and imaging all the time. The Hubble deep field images are full of accidental geometries, background objects appearing to interact with foreground ones, shapes that suggest relationship where none exists. The gap of Hoag's object is not large, angularly speaking. From Earth, the entire galaxy subtends a small angle. The gap within it subtends less. For another ring galaxy, specifically a ring galaxy, not just any smear of light, to appear centered in that gap, in those images, is the kind of coincidence that the universe produces without apparent effort and without any interest in what we make of it. What to make of it is probably nothing. It's a background object, a different mystery, a different set of unanswered formation questions, a different population of stars and gas and dark matter doing its own thing at its own distance, indifferent to the fact that it appears from here to be nested inside the gap of a closer and already strange galaxy. The universe is not arranging these things for effect, that much is certain, or nearly certain, which at cosmological scales might be the best available precision. But the image exists. The alignment is in the data. Somewhere in the photographic record of Hoag's object there is a frame in which two ring galaxies occupy the same small patch of sky, one impossibly far behind the other, the gap of the closer one framing the disk of the further one with a tidiness that no physics required, and no physics produced intentionally. It's just what was there when someone looked. The isolation of Hoag's object, the absence of companions, the lack of neighbours doing anything measurable to its structure, is one of its more persistent features. Most galaxies accumulate relationships over time. This one seems to have arrived or remained alone. The observable universe contains somewhere between 1 and 2 trillion galaxies. That estimate has shifted over the years. It was closer to 200 billion for a long time. Then a 2016 study using deeper Hubble data revised it upward by roughly a factor of 10, which is a significant revision by any standard. The number is still uncertain. It depends on how you count objects at the edges of detectability, how you handle the faint dwarf galaxies that outnumber large ones by a wide margin, how you deal with the fact that our instruments can only reach so far before the signal degrades past usefulness. 1 to 2 trillion. Sit with the low end of that for a second. 1 trillion galaxies. Ring galaxies, proper ones, with a defined annular structure and a nucleus, make up somewhere around 0.1% of observed galaxies in large surveys. That fraction varies depending on the survey's depth and the classification criteria used, but 0.1% is a reasonable working figure. 1 in 1,000 roughly. Apply that to 1 trillion and you get 1 billion ring galaxies in the observable universe alone. So rings aren't rare the way a specific person is rare, or the way a particular set of circumstances converging on a Tuesday afternoon is rare. They're rare the way left-handedness is rare, unusual enough to notice, common enough that you'll encounter plenty in a lifetime of looking. Hoag's object is not rare because it's a ring galaxy. It's rare because of the combination. The near-perfect circularity of the ring, most ring galaxies show distortions, asymmetries, evidence of the messy collision that produced them. Hoag's ring is almost eerily complete, like someone drew it with a tool rather than a catastrophe. The gap is unusually clean and unusually wide. The nucleus is unusually compact and symmetric. There are no obvious tidal features, no detectable companion, no kinematic evidence of a recent major interaction. Each of these properties, taken individually, is unusual but not shocking. Together they form a combination that doesn't appear often, maybe doesn't appear anywhere else in the surveyed sky with this particular convergence of features. I've seen Hoag's object compared to other ring galaxies in papers, and the comparison is always slightly awkward, like trying to describe one specific rock by referencing rocks in general. The category exists, the object fits the category's minimum requirements, but the object is doing something the category doesn't fully capture. The rarity is combinatorial, that's the right way to think about it. And combinatorial rarity is genuinely strange because it doesn't reduce to any single unusual property. It lives in the relationship between properties, in the specific configuration that resulted when whatever happened, happened. There is a useful analogy here, maybe, a deck of cards. Any specific hand dealt from a shuffled deck is astronomically unlikely. The exact sequence of 52 cards in a freshly shuffled deck has never occurred before, and will essentially never occur again. But we don't find shuffled decks remarkable because we're not attached to any particular sequence. We'd only find it remarkable if we had specified in advance what sequence we were looking for, and then got it. Hoag's object is remarkable because astronomers had in effect specified in advance what a well-formed ring galaxy should look like, and Hoag's object matches that specification more completely than almost anything else found since. That's not cosmic intention. It's just the difference between a meaningful coincidence and a random one, and where that line sits is partly a question of what you were measuring before you looked. Surveys matter here. The fact that Hoag's object is known at all, that it was noticed in 1950 and has been studied since, is itself a function of how humans have chosen to look at the sky. The surveys that produced the photographic plates Hoag was working through were not designed to find peculiar galaxies. They were designed to map the sky comprehensively at whatever resolution the technology allowed. Hoag's object appeared because it was in the survey region and bright enough to register. How many similar objects exist in regions not yet surveyed, or at distances that put them below current detection thresholds, is genuinely unknown. There could be others, probably are others. The observable universe is large enough to contain 1 billion ring galaxies. Some fraction of those will have properties approaching Hoag's combination, and some smaller fraction will match it closely, and some very small number might exceed it in terms of circularity or gap width, or the cleanness of the stellar population separation. We haven't found them yet. That doesn't mean they are not there. What it means practically is that Hoag's object has been studied in relative isolation, as a specimen without close analogues, which makes interpretation harder. A single unusual object invites speculation. A population of similar objects would invite statistical analysis, pattern recognition, the kind of comparative work that tends to produce more constrained conclusions. With one clear example and a handful of rough approximations elsewhere in the literature, the theorizing stays loose. The rarity, then, does two things simultaneously. It makes Hoag's object interesting, worth studying, worth modelling, worth the observational time it's accumulated over 70 years. It also makes it hard to study well, because the tools of astrophysics work best on populations, and Hoag's object resists being a population. It keeps being a specific thing. One object, one gap, one ring, one old yellow core sitting alone in Serpens, doing whatever it's been doing for the last 600 million years while the light from it crawls toward an audience it had no way of anticipating. The ring has been building stars, was building them in the light we're seeing for long enough that the question of how much longer it can keep doing so starts to feel relevant. Stellar populations age, gas runs out. The blue doesn't last forever, and what comes after it is a different kind of galaxy than the one currently visible. Light covers about 9.46 trillion kilometers in a year. That's not intuition friendly. Nothing about that number maps onto lived experience, and I'd argue it's not supposed to. It's a unit, a ruler. What matters is what you measure with it. Hoag's object spans roughly 100,000 light-years in its visible disk. The ring itself, outer edge to outer edge, stretches closer to 120,000. So, light crossing the ring takes 120,000 years. The Earth is 4.6 billion years old. Do that division, 120,000 into 4,600,000,000, and a signal crossing the ring from one side to the other could make that trip roughly 38,000 times over during the lifespan of our planet. One crossing is not a long time at cosmic scales, except it's also 120,000 years, which is longer than Homo sapiens has existed as a species. Scale does this. It makes both numbers true simultaneously and leaves you holding the contradiction. What this means physically for the stars in the ring, for the structure of the galaxy as a functioning system, is that different parts of Hoag's object are causally isolated from each other on human timescales, and nearly isolated even on longer ones. A star forming on one side of the ring has no knowledge of, no connection to, no influence over, a star forming on the opposite side. They orbit the same centre. They are part of the same gravitational system. But any signal, any disturbance, any change propagating from one to the other travels at the speed of light, which means a disturbance originating on one edge of the ring reaches the far edge 120,000 years later, give or take. The ring is not a community, it's a coincidence of orbit. Stars are arranged in a circle because the circle is the stable solution, not because they're in any meaningful communication with each other. I find this genuinely strange, and I've been thinking about this galaxy for, well, long enough that I should probably be less surprised by it. But the image of thousands of stars forming in coordinated-looking silence, each one isolated from its apparent neighbours by distances that swallow human history whole, that image doesn't get less strange with familiarity. The core adds another dimension to this. The distance from the ring to the core, from the inner edge of the ring to the centre of the nucleus, is somewhere around 40,000 to 50,000 light-years, depending on the measurement. A star forming in the ring right now, emitting a photon aimed directly at the core, won't have that photon arrive until 40,000 years from now, minimum. The core's gravitational influence reaches the ring, obviously. Gravity propagates, the orbital dynamics work. The ring exists because of the mass distribution anchored at the centre. But information, in the relativistic sense, moves at light speed. Events at the ring are invisible to the core for tens of thousands of years after they occur. They share a galaxy the way two people share a continent. Technically true, practically meaningless for most purposes. The new stars in the ring will be born, will spend millions of years on the main sequence burning hydrogen into helium, will evolve off that sequence into red giants or, for the most massive ones, will explode in supernovae, scattering heavy elements into the surrounding gas, seeding the conditions for the next generation of star formation. All of this will happen, is happening, has happened already in the light we're not yet receiving. Before a photon from those events reaches the core, something about that deserves sitting with for a moment before moving on. The ring stars are doing their physics in a kind of enforced solitude, separated from the core not just by the gap, but by the deep time it takes for anything to cross that distance. Whether that isolation is part of why the structure has lasted as long as it has, or irrelevant to it, isn't obvious. Most things in the universe that aren't in equilibrium either collapse or disperse. That's not a law with a name attached to it. It's more like a tendency so pervasive it barely needs stating. Gas clouds that aren't dense enough to collapse against their own thermal pressure just expand into the surrounding medium and vanish. Structures that form by chance without a stabilizing mechanism get pulled apart by tidal forces, orbital decay, the slow grind of dynamical friction. The universe is not a museum. It doesn't preserve things that don't have a physical reason to persist. Hoag's object has been preserving itself for a long time. How long exactly is hard to pin down, and the estimates in the literature are not uniform. The stellar population in the ring, those blue-white stars, the ones that make the ring visually distinctive, suggests active or recent star formation, which constrains when the ring structure must have been in place. You need a stable ring before you get star formation distributed evenly around it. The stars currently visible in the ring have masses that imply lifetimes of a few to several hundred million years for the more modest ones, shorter for the most luminous. If those stars formed in the ring was already a ring when they formed. Work backward from the stellar ages, add the time required for the ring to establish its current geometry, and you arrive at a structure that has been maintaining something close to its current form for, conservatively, several hundred million years, possibly longer. Several hundred million years is long enough for everything to go wrong multiple times over. The specific problem with the ring of stars, as opposed to, say, a disk or a spiral arm, is that a ring is a narrow structure. Stars in a disk are spread across a broad self-reinforcing distribution, where the collective gravity of the disk itself helps maintain orbital regularity. Stars in a ring are concentrated in a thin annulus, with empty space on either side. That geometry is less self-stabilizing. Small perturbations, a passing satellite galaxy, an uneven distribution of dark matter, just the slow accumulation of internal gravitational interactions between the ring's own stars, can thicken the ring, distort its circularity, cause it to precess or dissolve into a more uniform distribution around the nucleus. For the ring of Hoag's object to stay as circular as it appears, and as narrow, over hundreds of millions of years, something has to be managing the perturbations, or the perturbations have been unusually absent. One of those two things is true, and figuring out which one matters for understanding what the ring actually is, whether it's a temporary structure caught at a particularly stable moment, or something with a more durable physical basis. The dark matter halo is the obvious candidate for the stabilizing role. In most galaxies, the dark matter halo is far more massive than all the visible stars and gas combined, typically by a factor of 5 to 10, sometimes more. Its gravitational influence shapes how the visible matter moves, determines which orbital configurations are stable and which aren't, and can, in principle, create conditions where a ring at a particular radius is energetically favored over adjacent configurations. If the halo of Hoag's object has a particular shape, spherically symmetric in a specific way, with a density profile that produces a local minimum in the effective gravitational potential at roughly the ring's radius, then the ring isn't fighting against the galaxy's overall structure to maintain itself. It's sitting in a groove. The groove is invisible, made of dark matter, but it's real in the sense that the ring's persistence is real. This is the model that makes the most intuitive sense to me, for whatever that's worth. But I should be careful here. Intuitive sense and physical correctness are not the same thing, and the history of cosmology is full of cases where the intuitive explanation turned out to miss something important. The dark matter stabilization model is plausible. It hasn't been confirmed with enough observational constraint to call it settled. There's another angle on the stability question that I keep coming back to, which is less about the mechanism and more about the baseline assumption. When we call Hoag's object stability surprising, we're implicitly comparing it to an expected rate of disruption. But that expected rate is calculated from the average galaxy, from the statistical properties of the galaxy population as a whole, which includes galaxies in clusters, galaxies with active companions, galaxies undergoing mergers, galaxies in environments with high rates of gravitational harassment from passing objects. Hoag's object is isolated, genuinely isolated, no obvious companions, no cluster environment, no nearby galaxies doing anything measurable to its structure. An isolated galaxy in a low-density environment has a much lower expected rate of external perturbation than the average. The stability might be less mysterious than it looks once you account for the fact that nothing has been hitting it. That reframing doesn't fully resolve the question. Internal dynamics can disrupt a ring without any external help, but it shifts the emphasis. The ring's persistence might not require a special stabilizing mechanism. It might just require the absence of disruption for long enough, which Hoag's object, sitting alone in a quiet corner of Serpens, has apparently had. Star formation complicates this further. The ring isn't just a collection of old stars in stable orbits. It contains active star formation, or did when the light left, which means gas. A ring that contains gas is dynamically different from a ring that contains only stars. Gas loses energy through radiation, through collisions between gas clouds, through the dissipative processes that make it behave differently from collisionless stellar populations. Gas wants to settle. It wants to find the lowest energy configuration available to it and stay there. In most galaxies, that means gas flows inward, accumulates in the nucleus, feeds star formation at the center. In Hoag's object, the gases was concentrated in the ring, forming stars there rather than in the nucleus. The nucleus is quiescent, the ring is active. Whatever is keeping the gas in the ring rather than allowing it to migrate inward is part of the same stability question. A potential barrier, maybe, a local minimum in the gravitational potential that traps gas at the ring radius the way a bowl traps water. The dark matter halo again, possibly. A resonance condition between the orbital dynamics of the ring and some property of the underlying mass distribution. These are not exotic ideas. They appear in models of other ring galaxies and of barred spirals where gas accumulates at resonance radii. The application to Hoag's object is speculative in detail, but not in principle. The reason this all matters, and I realize this section has been fairly technical, more so than I intended when I started writing it, is that the stability of Hoag's object is not just a curiosity, it's a constraint. Whatever formation scenario produced this galaxy has to explain not just how the ring formed, but why it's still here, still circular, still producing stars after the time that has elapsed. A formation model that produces a ring but then dissolves it in 100 million years doesn't match the observation. The observation is a stable ring. The model has to account for the stability, not just the origin. That's a tighter constraint than it sounds. It rules out some scenarios. It makes others more specific in their requirements. It means the gap, the ring, the nucleus, the dark matter halo, the isolation. All of these things have to fit together into a single coherent physical history that ends with what we observe. Pulling on any one thread changes the tension in the others. Nobody has pulled them all into alignment yet. The ring is stable, or appears stable in the light we're receiving. What that same ring looks like from a vantage point 600 million light-years closer, what it looks like right now, tonight, in whatever sense tonight applies across that distance, is a different question, and not one with a retrievable answer. The light reaching us from Hoag's object is 600 million years old, not approximately, not as a rough order of magnitude. 600 million years, give or take the uncertainty in the distance measurement, which is itself a few percent, so call it somewhere between 575 and 625 million years. The blue stars visible in the ring left that light behind before the Cambrian explosion, before fish, before anything with a spine had figured out how to exist. The planet receiving it now looks almost nothing like the planet that was here when the light departed. So when we talk about what the blue stars are doing, present tense, as if we're watching, we're doing something slightly dishonest. Not wrong exactly. The light is real, the physics encoded in it is real, but present tense implies simultaneity, and there's no simultaneity available across that distance. What we're actually discussing is what the blue stars were doing 600 million years ago, as recorded in light that has spent the entire history of complex life on Earth crossing the distance between there and here. I keep catching myself writing "are" instead of "were" and then leaving it, because "were" makes everything feel more distant than it needs to. The stars existed, the physics was real, the tense is just a problem of language, not of the science. Blue stars, O and B type, the massive ones, burn hot and fast. The most massive among them, the ones producing the brightest blue-white light, have main sequence lifetimes of a few million years. A few million. Against the 600 million years the light has been travelling, a massive blue star in the ring of Hoag's object could have formed, lived its entire life, and exploded in a supernova. All of that could have happened, start to finish, during the first 1% of the light's journey to us. We're not seeing those stars anymore. We're seeing their light from a moment early in their lives, a snapshot taken before the story finished. The less massive blue stars last longer. B-type stars can persist on the main sequence for tens to hundreds of millions of years, depending on mass. Some of the stars currently visible in the ring, visible in the sense of contributing to the blue light we measure, will still be burning today, in the galaxy's actual present. Others won't. The ring as we see it is a composite, a superposition of stars at different stages, some long dead by now, some still going. We can't separate them. The image doesn't come with timestamps. What's probably happened to the ring in the 600 million years since this light left is some version of aging. The most massive stars are gone. Supernovae, remnants, the heavy elements they produced scattered into the surrounding gas. The moderately massive ones are in various stages of post-main sequence evolution, swelling into giants, shedding mass, cooling. The ring's colour, integrated across all its stars, has almost certainly shifted. Less blue-white, more yellow-white maybe, or unevenly coloured, if star formation has been ongoing, and new massive stars keep refreshing the blue end of the population. Whether star formation has continued is genuinely unknown. The gas supply in the ring, the raw material for new stars, was clearly sufficient 600 million years ago to sustain active formation. Whether it's been replenished, or depleted, or whether the ring has cycled through multiple generations of star formation since then is not something the current data addresses. The observations constrain what the ring was. The ring's present state is, bluntly, inaccessible. There might be a version of Hoag's object that a civilization closer to it could observe right now, a civilization 300 million light-years away, say, splitting the distance, working with light only 300 million years old, and they would see a ring at a different stage. Older in some stars, possibly younger in others if new formation episodes have occurred. A different colour balance, maybe a slightly different geometry if the ring has evolved structurally. That observer's Hoag's object and our Hoag's object are the same physical galaxy at different moments in its history, and neither of us gets to compare notes. This is the thing about deep sky objects that I find genuinely hard to hold in mind consistently. Not the distances, those are just numbers, but the fact that every object in the deep sky is a historical document, not a live feed. We've built entire cosmological models on historical documents. The cosmic microwave background is a document from 380,000 years after the Big Bang. The most distant galaxies in the Hubble Ultra Deep Field are documents from when the universe was less than 1 billion years old. The method works, the science is solid. But Hoag's object specifically, with its blue ring and its open formation questions, sits in a strange position where the thing we most want to know, is the ring stable? Is it still forming stars? Has it changed? Is precisely the thing the light cannot tell us. The blue we're seeing might be, in the galaxy's actual present, a ring of aging yellow-white stars slowly quieting down, or the same vivid blue, refreshed by ongoing star formation, or something structurally different if a perturbation has occurred in the intervening 600 million years. The ring keeps its secret simply by being far away. No drama in that, just physics and distance and the finite speed at which information moves through space. 600 million years is long enough for a lot to change. Long enough, actually, for the galaxy's isolation itself to have changed. Whether Hoag's object is still alone, still undisturbed, or whether something has entered its vicinity in the time the light has been travelling, that question has the same answer as the rest of them. Most large galaxies are social in a specific gravitational sense. The Milky Way has the Magellanic Clouds, 2 irregular dwarf galaxies, visible from the southern hemisphere as detached patches of the Milky Way, close enough that their gravitational interaction with our galaxy is measurable and ongoing. Andromeda has a retinue of satellite galaxies, at least 20 confirmed, probably more at lower masses below current detection limits. Even galaxies that appear isolated in casual observation tend, under deep imaging, to reveal streams of tidally stripped stars, faint shells of material from past mergers, the structural residue of relationships that have accumulated over billions of years. Galaxies collect companions. It's what they do. The gravitational potential of a large galaxy acts like a slow trap. Smaller objects passing nearby get captured, their orbits decaying over time, until they either merge completely or settle into long-term satellite orbits that can persist for billions of years. The Milky Way is currently in the process of absorbing the Sagittarius dwarf galaxy, which has already passed through the Milky Way's disk multiple times, leaving tidal streams that wrap around the entire galaxy. The process is ongoing, messy, drawn out over hundreds of millions of years. Hoag's object shows none of this. No confirmed satellite galaxies, no tidal streams in the deep images, or nothing unambiguous, nothing that clearly traces back to a companion rather than internal structure or imaging artifacts. No obvious companion galaxy in the vicinity that could account for the ring's formation and is still decelerating away from the encounter. The galaxy sits in a region of relatively low galaxy density, in an environment that simply hasn't provided the same accumulation of interactions that most large galaxies experience over their lifetimes. This isolation is partly what makes the formation question so difficult. The most popular model for ring galaxy formation, a nearly perpendicular collision with a companion, requires a companion. If there's no companion, the model has to explain where it went. Companions that pass through a galaxy don't vanish, they accelerate, turn around under gravity, eventually return. Or they escape entirely if the encounter velocity exceeded the escape speed, but an escaped companion would still be detectable as a receding galaxy in the vicinity, showing a relative velocity consistent with the encounter geometry. Nothing like that has been found. That's not definitive. Surveys have limits. Faint dwarf galaxies can be missed. A low-mass intruder might have been tidally destroyed in the encounter, and its remains dispersed too finely to detect. These are legitimate caveats. But the absence is notable enough that it keeps showing up in papers as a problem to be addressed rather than a detail to be footnoted. The isolation also raises a question I find harder to shake than the formation question, which is, what produced the conditions for this galaxy's isolation in the first place? Galaxy clustering is not random. Galaxies form in the dense nodes and filaments of the cosmic web. The large-scale structure of the universe and their local environments are determined by that structure. An isolated galaxy is typically in a region of low matter density, a void or a void-adjacent environment where the cosmic web is thin. Hoag's object's isolation might simply reflect where it formed. Low-density neighborhood, fewer passing galaxies, fewer opportunities for the interactions that most large galaxies accumulate, which would mean the isolation isn't a mystery at all, just a location. Some galaxies form in rich clusters and spend their lives surrounded by thousands of neighbors. Some form in the spaces between filaments and spend their lives almost entirely alone. Hoag's object drew the latter, but that reframing doesn't fully settle it, because an isolated galaxy that still managed to develop a ring, still experienced whatever event produced that structure, did so with limited external material to work with. The ring had to come from somewhere. The gas forming those blue stars came from somewhere. In an isolated galaxy with no recent companions, the origin of that material is more constrained, not less. The isolation tightens the problem rather than relaxing it. There's something I keep returning to in the images, the specific quality of the empty space around Hoag's object in deep exposures. Around most large galaxies, the background isn't truly empty. There's faint extended light from the galaxy's own halo, from unresolved distant galaxies, from the general glow of the surrounding environment. Hoag's object has a halo too, faint and extended. But the surrounding field has a particular sparse quality, a visual quietness. The galaxy sits in it the way an object sits on a cleared surface, not dramatically alone, just without the clutter that usually accumulates. That's an aesthetic observation, not a scientific one. I'm aware of that. But sometimes the aesthetics of an image are telling you something real about the physics underneath. Isolation affects more than just the formation history. A galaxy that spends billions of years without significant external perturbation evolves differently than one embedded in a rich environment. The rate of star formation, the structure of the gas reservoir, the long-term fate of features like rings and gaps. What Hoag's object might look like in another few billion years, left to its own dynamics in an empty neighborhood, is a different kind of question than how it formed. There's a diagram I remember from an undergraduate cosmology textbook, not a particularly good textbook, spiral-bound, the kind that gets photocopied until the images go grey, showing a galaxy's rotation curve. On the horizontal axis, distance from the galactic centre. On the vertical axis, orbital velocity. The expected curve, if only visible matter existed, drops off with distance the way planetary orbital speeds drop off from the Sun. Mercury moves fast, Neptune moves slow. The relationship is clean and follows directly from how gravity works when mass is concentrated at the center. The observed curve for most galaxies is flat, embarrassingly stubbornly flat. Stars at the outer edges of a galaxy orbit at roughly the same speed as stars much closer in. That flatness is not explainable without invoking a large amount of mass that isn't visible. Dark matter, distributed in a halo extending far beyond the visible disk, its gravitational influence propping up the outer rotation curve like a hand under a sagging shelf. This was not a controversial finding by the time I encountered it. Vera Rubin had measured flat rotation curves in the 1970s, building on earlier work by Fritz Zwicky in galaxy clusters, and by the 1990s the dark matter halo was standard equipment in any model of galaxy structure. The textbook presented it as settled. It mostly is settled, in the sense that something is doing what dark matter does. The rotation curve data alone across thousands of galaxies is hard to argue with. What dark matter actually is, physically, what particle or particles constitute it, why it doesn't interact electromagnetically, whether it has any self-interaction, that part is not settled at all, and the absence of a confirmed dark matter particle detection after decades of increasingly sensitive experiments is, depending on your disposition, either a puzzling gap or a slow-building crisis. For the purposes of Hoag's object, the relevant question isn't what dark matter is, it's what shape it's in. Halos are not all the same. The distribution of dark matter around a galaxy depends on the galaxy's formation history, how it assembled, whether it experienced major mergers, how its baryonic matter, the normal stuff, stars and gas, redistributed itself over time and fed back into the halo's structure through processes like supernova-driven outflows. A galaxy that formed quietly in isolation, without major mergers, tends to have a different halo profile than one that assembled through multiple large collisions. The halo carries a record of the galaxy's history in its density profile, the way a tree carries a record of dry years and wet years in its rings, not readable at a glance, requiring careful measurement to decode, but there. For most galaxies, the halo is roughly spherical and follows a density profile that peaks sharply toward the center and falls off in a predictable way with radius. The NFW profile, Navarro, Frank and White, from a 1996 paper that became one of the most cited in astrophysics, describes this shape, derived from cosmological simulations of dark matter halo formation. It works reasonably well for a lot of galaxies. It has known problems at small scales, in dwarf galaxies especially, where the predicted central density cusp is often not observed. Theorists have been arguing about this for 30 years. For Hoag's object, the halo profile is not well constrained. The measurements that would constrain it, detailed rotation curve data, weak gravitational lensing maps, satellite kinematics, are either unavailable at the required precision or absent entirely because the galaxy has no satellites to use as kinematic tracers. What can be said is that the halo has to be doing something consistent with the ring's persistence. A halo that produced strong non-axisymmetric perturbations would have distorted the ring. The ring isn't distorted. So either the halo is unusually symmetric, or the perturbations are small enough that they haven't accumulated into detectable distortion over the ring's lifetime, or the ring is younger than it looks and hasn't had time to respond to whatever asymmetries the halo contains. 3 possibilities again, each requiring different assumptions, none of them definitively ruled out. What a spherically symmetric halo does practically for a ring structure is provide a potential well, a gravitational landscape that has no preferred direction, no bar, no lopsidedness, no tidal pull from a companion dragging material to one side. A ring of stars embedded in a perfectly spherically symmetric potential will stay a ring indefinitely, each star completing its orbit in a time determined only by its distance from the centre, the circular symmetry of the potential preserving the circular symmetry of the ring. This is idealized. No real halo is perfectly symmetric, but the closer to spherical symmetry the halo is, the longer a ring can persist before perturbations accumulate into visible distortion. The isolation of Hoag's object feeds into this. A galaxy without companions has a halo that hasn't been significantly disturbed by external tidal forces. The halo can settle into a more symmetric configuration than a galaxy embedded in a rich cluster environment, where the gravitational tugging from neighbours continuously stirs things up. Isolation, in this sense, is protective. It lets the halo be boring in the specific way that's good for ring stability. I want to be clear that this is a plausible narrative, not a confirmed one. The data on Hoag's object's dark matter halo is thin. I'm describing what would be consistent with the observations, not what has been demonstrated by them. These are different things, and I keep having to remind myself of that distinction when thinking about this galaxy, because the consistent narrative feels so much more satisfying than the honest answer, which is, we don't know what the halo looks like in detail, and without that knowledge, the stability story has a large gap in its middle. Here's what dark matter modelling does well, and where it starts to feel fussy. In simulations, you can set up a halo with a particular profile, drop in a ring of stars and gas at the appropriate radius, and watch what happens over several billion simulated years. The ring either persists or it doesn't. If it persists, the halo profile is consistent with the observation. If it doesn't, you adjust the profile and try again. This is the standard approach, and it's produced real insight in other systems. It works for understanding spiral arm lifetimes, bar formation, the response of galaxy disks to satellite perturbations. For Hoag's object, nobody has run a fully constrained version of this simulation, as far as I can tell. There are simulations exploring ring galaxy formation in general, and some that specifically try to reproduce Hoag's morphology, but the dark matter component in these is often a background potential rather than a fully self-consistent live halo, and the parameter space explored is limited. The computational cost of running large numbers of high-resolution n-body simulations with live dark matter halos is non-trivial, and Hoag's object is a single unusual galaxy that doesn't obviously generalize to a broader population. Funding follows populations, so the dark matter story for Hoag's object remains qualitative, suggestive. The halo is there, it has to be there. The rotation curve would be wrong without it. Its shape is probably conducive to ring stability. The ring's persistence implies as much. But the specific properties of the halo that would distinguish between competing formation models, that would tell you whether the ring formed from a collision or an internal instability or a merger, are not known. The dark matter is doing something. It's doing it invisibly, in a galaxy 600 million light-years away, with instruments that weren't designed to answer this specific question. The visible structure of Hoag's object, the core, the gap, the ring, is the surface of something much larger and more massive that can't be seen. The halo extends beyond the ring, far into the darkness outside the visible galaxy, exerting gravitational influence on material that's too sparse to show up in optical images. If you could somehow illuminate the dark matter halo of Hoag's object, make it visible, you'd see a roughly spherical blob of material dwarfing the visible galaxy, the ring and core embedded inside it like a small bright decoration inside a large dim cloud. That cloud is most of the galaxy's mass. The stars and gas, the things we take photographs of, the things that emit light, the things we use to infer everything else, are a minority component. maybe 15% of the total mass, maybe less. The rest is dark matter, structureless and silent, shaping everything without participating in any of the processes we can directly observe. It made the shape, or allowed the shape, or preserved the shape once something else produced it. The specific role is unclear, the contribution is enormous, and the evidence for it is entirely indirect. What Hoag's object looks like from outside, the full structure, the halo, the faint extended light beyond the ring, is different from what the clean optical images suggest. Deep imaging pulls in details that shorter exposures miss, and some of those details complicate the picture in ways that are harder to set aside than the main structure. Old stellar populations don't announce themselves. They just glow, warmly, steadily, without the urgent blue-white intensity of young stars burning through hydrogen at a rate they can't sustain. The core of Hoag's object is doing this. Glowing yellow-orange, the integrated colour of billions of stars that have settled into the slower metabolisms of middle and late stellar age, the most massive among them already long dead, the remainder burning at rates they can maintain for billions of years more. This is what a galaxy looks like when it stops forming stars, not dead, just finished with that particular phase. Elliptical galaxies are the canonical example. Large, smooth, yellow-orange, dominated by old stellar populations, their star formation having shut down billions of years ago through some combination of gas exhaustion, feedback from central supermassive black holes, and the heating of the surrounding gas reservoir to temperatures where it can no longer cool efficiently enough to collapse into new stars. The details of exactly how star formation shuts down and why it stays shut down is one of the more active debates in galaxy evolution. The short version is, something heats or removes the gas, and without cold gas, you don't get stars. The core of Hoag's object looks like a small elliptical, compact, symmetric, red-yellow in colour, no obvious signs of ongoing star formation in any wavelength. Whatever process extinguished star formation there did so a long time ago. The stellar population's colour implies ages of several billion years at minimum, possibly much older. Here's what I find quietly strange about this. The core stopped forming stars. The ring didn't, or hasn't yet, as of the light we're receiving. These two regions of the same galaxy are in completely different phases of evolution simultaneously. The core has moved through whatever transition shuts star formation down and come out the other side into a long, stable quiescence. The ring is still in the active phase, both sitting inside the same gravitational structure, separated by 30,000 light-years of relative emptiness. In typical galaxy evolution, the inside quenches first. Star formation migrates outward over time as the inner regions exhaust their gas or have it heated by central feedback. A galaxy building stars preferentially in an outer ring, while its centre sits quiescent is not by itself impossible. Outside-in star formation does occur in specific circumstances, but the degree of separation in Hoag's object, the sharpness of the boundary between the quenched core and the active ring, enforced by that gap, that's not what outside-in star formation normally produces. Usually there's a gradient, a slow transition, not a clean break. The gap is doing something to maintain that boundary, or the gap is the boundary. Hard to say which came first. Supermassive black holes live at the centres of most large galaxies. The Milky Way's Sagittarius, a star, has a mass of about 4 million solar masses. Andromeda's is larger, somewhere between 100 million and 200 million solar masses. The relationship between black hole mass and galaxy bulge mass is surprisingly tight across a huge range of galaxy types. Tight enough that the two things clearly co-evolved, even though the black hole sphere of direct gravitational influence is tiny compared to the galaxy as a whole. The mechanism coupling them is thought to involve feedback, energy and momentum injected into the surrounding gas by the black hole during periods of active accretion, heating the gas reservoir and suppressing star formation across scales far larger than the black hole's direct reach. Hoag's object presumably has a supermassive black hole in its core. There's no strong detection, no obvious active galactic nucleus signature in the existing data, no bright central point source indicating active accretion. The black hole, if it's there, is quiet. Starved, probably, in the way central black holes tend to be quiet in galaxies that stopped feeding them gas a long time ago. The core has nothing much left to give it. Whether the black hole's past activity contributed to shutting down star formation in the core, and whether that shutdown then somehow propagated outward to create or maintain the gap, is speculative. The connection is plausible in broad strokes. In detail for this specific galaxy, it hasn't been worked out, the data doesn't resolve it. What the core does offer, quietly, is a kind of timestamp. The colour and spectral properties of the old stellar population constrain when star formation stopped. Stellar population models, which predict how a population of stars of a given age and composition should look, suggest the core's stars are old enough that whatever happened there happened well before anything visible happened in the ring. The core's history and the ring's history are not synchronized. They're chapters from different eras, bound together in the same object. A galaxy carrying two different eras simultaneously in its structure. The core's long quiet and the ring's ongoing, or recently concluded, burst of formation. Something connected them once through whatever event produced the ring. Now they orbit a common centre, each doing its own thing, separated by a gap that neither one produced alone. The gap, the core, the ring, they fit together into something that looks almost like a sequence when you describe it. But sequences imply causes, and the causal chain here is broken in at least one place, probably more. What the data can say about that broken chain, and what it honestly cannot say, is worth being precise about. Astronomy is, at its core, a science of single frames. You point an instrument at something, collect photons for some duration, record what arrived. Then you do it again, maybe with a different instrument, or a different wavelength, or a longer exposure time. Each observation is a frame. String enough frames together and you might catch something changing. A variable star pulsing, a supernova brightening and fading, a planet transiting. But for objects at cosmological distances, change happens on timescales so vast that the concept of watching something evolve basically doesn't apply. You get a frame, that's the deal. With Hoag's object, the frame problem is acute in a specific way. The questions the galaxy raises are almost all questions about process. How did the ring form? What maintains the gap? Why are the stellar populations so cleanly separated? Process questions want time series data. They want before and after. Hoag's object offers neither. It offers a single, very detailed snapshot of an outcome, and from that snapshot you are asked to reconstruct a history stretching back billions of years. The multi-wavelength data helps, up to a point. Optical imaging shows the stars, their distribution, their approximate colours, the morphology of the ring and core and gap. Infrared data probes dust and cooler stellar populations, adding depth to the optical picture. Radio observations, specifically the 21 centimeter hydrogen line, map the distribution of neutral atomic hydrogen gas, which traces the raw material for star formation and often extends far beyond the visible stellar disk. X-ray observations, if available, would reveal hot gas and any active nucleus. Each wavelength is a different kind of frame, sensitive to different components of the same object. For Hoag's object, the radio data is particularly interesting. Neutral hydrogen in ring galaxies often extends well beyond the optical ring, sometimes showing kinematic signatures, velocity patterns in the gas that carry information about the galaxy's dynamical history. Whether the hydrogen in Hoag's object shows anything unusual in its kinematics, anything pointing toward a specific formation mechanism, the published data is thin. The radio observations that exist are not high enough resolution to resolve the detailed velocity structure within the ring and gap regions cleanly. Higher resolution radio observations with something like the VLA or ALMA would probably add real constraint. Whether those observations have been made and not yet published or simply haven't been prioritized, I genuinely don't know. The deeper problem is that each frame, regardless of wavelength, is still a frame. It shows where things are and how bright they are. It doesn't show how they got there. The causal history, the sequence of events connecting the galaxy's formation to its current state, has to be inferred through modeling, through comparison with simulations, through the logic of what processes could have produced what's observed. That inference chain is long. Each step introduces assumptions. By the time you arrive at a conclusion, you're holding something that is consistent with the data, but not uniquely required by it. Multiple different histories can produce the same snapshot. This is a fundamental limitation of forensic science applied to the universe, and it shows up everywhere in astrophysics, not just in Hoag's object. But Hoag's object makes it unusually visible because the snapshot is so striking and the history so contested. A more ordinary galaxy raises the same epistemological problem in principle. In practice, ordinary galaxies fit known templates well enough that the inference feels secure. Hoag's object doesn't fit cleanly, so the inference stays exposed. More frames would help. Better frames, higher resolution, wider wavelength coverage, more sensitive to faint extended structure. Hoag's object has been imaged by Hubble. That data is genuinely beautiful and has added real detail to the optical picture. But Hubble can't do radio. And the radio data, the kinematic data, the detailed velocity structure that might point most directly toward the formation mechanism, that data is sparse. The file stays open partly because nobody has looked with quite the right instrument at quite the right sensitivity. That's a tractable problem in principle. Just a matter of telescope time and priority, and whether the community decides the question is worth the resources. What the existing data does constrain, what it rules out and what it leaves possible, is worth being careful about. The theories aren't all equally supported, even if none of them are fully confirmed, and the differences between them have implications for what Hoag's object actually is. Assume for a moment that nothing comes, no passing galaxy drifting close enough to pull at the ring's edges, no satellite falling in from the outer halo, no major perturbation from outside. Hoag's object left alone, which, given its isolated location in a low-density region of the universe, is not an implausible assumption. What does the galaxy look like in 1 billion years? 5 billion? What does physics, running forward without interference, do to a ring of blue stars surrounding a quiet yellow core? The blue stars go first. They're already going, in the sense that the most massive ones burn fast enough that their lifetimes are short even against the timescales of galaxy evolution. O-type stars, the hottest, most luminous, last maybe a few million years, before running out of hydrogen in their cores and expanding into supergiants, then exploding. Already in the 600 million years since the light we're receiving left Hoag's object, every O-type star visible in that ring image has lived and died multiple times over. Not multiple times individually, obviously, but multiple stellar generations could have cycled through in that time if star formation has continued. The point is the population turns over. The most brilliant contributors to that blue colour have the shortest leases. What remains after the most massive stars die depends on whether new ones form to replace them. Star formation requires cold, dense gas. The ring has gas, had gas, detectable in radio observations, but gases are consumable. Every star that forms depletes the reservoir slightly. Massive stars that explode inject energy back into the surrounding gas, which can either trigger new star formation by compressing nearby clouds or suppress it by heating the gas past the point where it can cool and collapse. The balance between these two effects, triggering versus suppression, determines whether star formation is self-sustaining or self-terminating. In most actively star-forming regions in nearby galaxies, the process is self-limiting over long timescales. The gas runs down, the star formation rate drops, the population ages. This isn't controversial, it's just thermodynamics and gas dynamics running their course. So the ring, without a fresh supply of gas from outside, probably fades. The blue dims, the stellar population, no longer refreshed by new formation, ages collectively, massive stars dying off, the remaining population shifting through yellow toward orange as billions of years accumulate. The ring doesn't disappear structurally, not quickly. The stars are still there, still orbiting, still a ring. It just stops being a blue ring and becomes something dimmer, redder, harder to distinguish from the surrounding dark. The gap might change too, and this part I find harder to think through cleanly. If the gas that maintained the ring's star formation depletes, and if the processes that cleared the gap were linked to whatever dynamics drove the ring formation, then the gap's long-term stability isn't guaranteed. Gas can migrate inward through various dissipative processes. Stellar mass loss from evolved stars returns material to the interstellar medium, and that material doesn't stay put. It gets pushed around by stellar winds, by the gravitational potential, by whatever residual dynamics are operating. Over billions of years, some of that material might drift inward, slowly populating the gap with a diffuse stellar component blurring the boundary. Or the dark matter halo's gravitational structure might be stable enough to keep the gap clear indefinitely. The gap might be a permanent feature of the gravitational landscape, not just a transient cleared region. In that case, the gap persists while the ring ages, and the galaxy evolves towards something that looks more like a faint ring of old stars surrounding a brighter old core. The color distinction between ring and nucleus reduced. Both populations older. The gap still present but less dramatically obvious because the structural contrast has softened. Neither of these trajectories is dramatic, no explosion, no sudden transformation. Just time doing what time does to stellar populations, cooling them, dimming them, shifting the color balance incrementally across millions of years until the galaxy, that was once striking enough to stop Art Hoag mid-classification, is something quieter, less visually arresting, possibly classifiable under a more ordinary category. The really long timescales are harder to think about and probably less useful for understanding what Hoag's object is. On timescales of tens of billions of years, stellar evolution in the ring will have run far enough that even the lowest mass stars begin exhausting their fuel. The universe is currently about 13.8 billion years old. The lowest mass red dwarf stars have lifetimes of trillions of years. They will outlast everything else by an enormous margin, burning so slowly and dimly that their contribution to a galaxy's total luminosity is tiny but persistent. A galaxy in the far future is a very faint, very red, very sparse collection of these long-lived embers. Hoag's object will get there eventually, if nothing disrupts it. The ring structure might still be detectable in the stellar distribution even when the stars themselves are dim red dwarfs. The orbital dynamics that maintain the ring don't care about stellar luminosity, only mass. A ring of dim red dwarfs, orbiting in the dark, maintaining their circular configuration around an old quiescent core. The gap's still present in the stellar density map, if not in any image a human eye could interpret. That's a long way from now, and it might not happen. Something might disrupt it before then, a passing galaxy, a merger, the expansion of the universe gradually loosening gravitational structures on the largest scales. But the physics, run forward without interference, produces something like that eventual quiet. A galaxy completing its long process of burning down, maintaining its strange shape until the shape is all that's left of what it was. The future is speculation, obviously. The present, or the 600-million-year-old present we have access to, is at least constrained by data. What that data can honestly say, versus what gets added by interpretation and narrative, is a distinction worth paying attention to in a case like this one. There's a specific texture to an unsolved problem that had been unsolved for a long time. It's different from a new problem, where the uncertainty feels provisional, temporary, a gap that will close once the right data arrives or the right person thinks about it carefully enough. A long unsolved problem has a different quality. It's been handled, turned over, examined from multiple angles by people who knew what they were doing. The uncertainty that remains isn't the soft uncertainty of an unexplored territory. It's the harder uncertainty of a territory that has been explored and still won't yield. Hoag's object has been in this second category for over 70 years. I want to be precise about what that means, because it's easy to romanticize it, to make the unsolved quality sound more profound than it is, to turn a stubborn astrophysics problem into something philosophical. It isn't philosophical. It's a galaxy with a ring and a gap and an unclear origin story, and the reason it's unclear is partly that the evidence needed to resolve it degraded billions of years ago, and partly that the observations available so far haven't been quite the right kind, and partly that the theoretical tools for distinguishing between formation scenarios are still being refined. These are practical limitations, not cosmic mysteries in the literary sense. They'll probably be resolved eventually, maybe by better radio observations, maybe by a well-designed simulation campaign, maybe by finding a closer analog galaxy that can be studied in more detail, but eventually hasn't arrived yet. And in the meantime, Hoag's object sits in the literature as an open file with a lot of annotations. What I find genuinely interesting, and I realize I keep saying genuinely, as if to ward off the suspicion that I don't mean it, which is a verbal tick I should probably drop, is not the mystery itself but the structure of the uncertainty. Each piece of the puzzle is individually somewhat constrained. The ring's stellar population gives a rough age bracket for when star formation occurred. The gap's width and cleanliness constrain the formation mechanism to some degree. The core's old stellar population establishes a lower bound on how long the central region has been quiescent. The lack of companions constrains the interaction history. These constraints exist. They're real. They rule things out. What they don't do is converge on a single consistent story. The constraints are individually loose enough that multiple histories remain compatible with all of them simultaneously. You need tight constraints, measurements precise enough that only one model fits all of them at once to close a problem like this. For Hoag's object, the constraints are overlapping, but not tight enough to exclude everything except one answer. Several models survive the full set of constraints. The file stays open. This is worth sitting with for a moment, because it's easy to read unsolved as ignored or abandoned, and that's not what's happening. Papers on Hoag's object have been published across 6 decades. The observational data has improved dramatically since Hoag's original photographic plate. Hubble imaging, multi-wavelength surveys, spectroscopic data on the stellar populations. The theoretical framework for understanding ring galaxies has developed substantially, with dedicated simulations and improved models of galaxy interaction physics. None of this has been idle. It's more that the problem is genuinely hard in a specific way. The formation event, whatever it was, happened long enough ago that the direct evidence is gone. What remains is the outcome, and outcomes can be produced by multiple paths. Forensic science deals with this constantly. The problem of equifinality, different causes producing identical effects, and the solution is usually to find the process evidence, the traces of how something happened rather than just what resulted. In astrophysics, process evidence at cosmological distances and billion-year timescales is either extremely faint, absent entirely, or requires a level of observational precision not yet achieved. Hoag's object is a case of equifinality at galactic scale. The outcome is clear and well documented. The process that produced it is hidden in a past that light from the galaxy hasn't fully reported on yet, and may never report on in the detail required. There's a paper from 2011, Finkelman and colleagues, if I'm remembering correctly, and I might be misremembering the year, that did a fairly comprehensive multi-wavelength analysis and came down cautiously in favour of a merger scenario, specifically a minor merger where a low-mass companion was absorbed and the disturbance triggered ring formation. The analysis was careful. The conclusion was framed with appropriate uncertainty. It didn't end the debate. Later work has continued to probe different aspects of the problem, and the field hasn't settled into consensus around any single model. I don't say this to criticize the researchers involved. The uncertainty in the conclusions reflects the uncertainty in the data, not any failure of rigor. Science working correctly looks like this sometimes, not convergence, but careful characterization of what can and can't be said given available information. The temptation is always to prefer the cleaner narrative, the resolved case, the mystery explained. The honest version is messier. Hoag's object has accumulated a particular kind of scientific attention over the years, not the sustained, well-funded attention of a major unresolved problem in fundamental physics, but the periodic, curious attention of researchers who find it interesting enough to spend some telescope time on, or to include in a survey of peculiar galaxies, or to use as a test case for a formation model they're developing for other reasons. This is a reasonable allocation of scientific resources. It's a single unusual galaxy, not a class of objects that demands urgent theoretical resolution. But it also means the observational coverage is somewhat piecemeal, good in some wavelengths and at some resolutions, thin in others. A dedicated multi-wavelength high-resolution observational campaign, the kind you'd design specifically to answer the formation question, with instruments chosen to probe the kinematics of the gas, the detailed stellar populations in the ring and gap, the outer halo structure, hasn't been done as far as I can find in the literature. Whether it should be done is a question of priorities and resources that the astrophysics community will answer in its own time. The James Webb Space Telescope can do things with infrared imaging and spectroscopy that previous instruments couldn't. Radio arrays like the VLA and MIR-K have improved resolution and sensitivity. The tools exist or are coming into existence that could genuinely tighten the constraints. Maybe the file closes in the next decade, maybe not. What the long uncertainty does, whatever its eventual resolution, is preserve a quality in Hoag's object that solved problems tend to lose. Once a formation mechanism is confirmed and the models agree and the textbooks are updated, the galaxy becomes a case study, illustrative, pedagogically useful, no longer a live question. It settles into the furniture of established knowledge. The particular quality of looking at it and not fully knowing what you're looking at, that quality disappears. I'm not arguing for keeping it unsolved. That would be a strange preference. The knowing is better than the not knowing for the purposes of understanding how the universe works. But there's something in the specific texture of looking at the image of Hoag's object, the ring, the gap, the quiet core, the background ring galaxy, sitting by accident in the gap's emptiness, and knowing that physics produced all of it and hasn't fully explained how, that is worth noticing before the explanation arrives. The not knowing has its own kind of presence. It makes the looking more careful, more attentive to what's actually there, rather than what you've already been told to see. The galaxy doesn't care, obviously. It rotates, it ages, it does its physics at 600 million light-years distance without reference to whether we've worked out its history. But the looking, the quality of attention brought to something that hasn't yielded, that's ours. And it might be worth holding on to even as the data improves. What the looking eventually settles into when the lights are low and the thinking slows is something quieter than a question and less than an answer. Just the fact of the distance and the light crossing it and the shape it describes when it arrives. 600 million light years. The numbers appeared enough times in this script that it risks becoming wallpaper, a figure you read past without it landing. So let me try once more, differently. The light we receive from Hoag's object left that galaxy before animals with eyes existed on Earth. Whatever was here when that light departed had no way to receive it. No apparatus for detecting photons, no nervous system to register the information encoded in the wavelength. The light travelled for the entire history of complex life on this planet, through the Cambrian, through the age of fish, through every extinction event, through the emergence of land animals, through the dinosaurs, through everything, and arrived here, now, at instruments built by the first species that could actually use it. That's not poetic framing. That's just the arithmetic of the distance. What the light carries is specific. The colour distribution across the galaxy's face, yellow at the core, blue-white at the ring, encodes the surface temperatures of stars, which encodes their masses and ages, which encodes something about the history of star formation in each region. The spatial distribution of the light encodes the structural geometry, the gap width, the ring's circularity, the nucleus's compactness. Spectroscopic data, where it exists, encodes radial velocities, chemical abundances, the kinematic state of the gas. Every photon that makes it into a detector is a data point in a message sent 600 million years ago by physics that had no intention of sending a message. The galaxy is indifferent to our reception of it. This should be obvious, but somehow keeps needing to be re-established, at least for me. Hoag's object is not waiting to be understood. It isn't patient or mysterious in any active sense. It's rotating in an empty neighbourhood, its ring aging, its core persisting in its long quiet, utterly regardless of whether anyone ever works out its formation history. The open file in the astrophysics literature is our problem, not the galaxy's. Distance in this context functions like silence, not the absence of signal. Clearly the signal arrives, the light reaches us, the data is real. More like the silence of a very large space, where sounds exist but are so attenuated by the distance they have travelled that they carry information without carrying presence. You know something happened. You can measure what. The thing itself is elsewhere, unreachable, doing whatever it's doing now in a present that won't reach you for another 600 million years. I keep thinking about what it would mean to actually be there. Not a useful thought, not scientifically productive, but hard to avoid after spending enough time with the images. To be somewhere in the vicinity of Hoag's object, close enough that the ring filled a significant portion of the sky. The ring is 120,000 light-years across. Even from a few million light-years away, it would be visible as a structure, not a point. A ring of blue-white star-forming regions surrounding an old yellow core, the gap between them dark and clear. From inside the ring, from a planet hypothetically orbiting one of the ring's stars, The core would be a distant concentration of warm light, like a compact elliptical galaxy seen from a considerable remove. The gap would be visible as a region of relative emptiness between your local neighbourhood and that distant concentration. The other side of the ring would be a faint arc of light, too dispersed to be dramatic but present, detectable on a clear night. It would look from inside like the loneliest kind of home. That's where this ends, not with an answer, because the honest answer is that the formation question is open, and the galaxy's present state is inaccessible, and the data is incomplete in specific ways that matter. Hoag's object is strange, stable, isolated, old in its core and young in its ring, separated from us by a distance that converts presence into record. What it is, physically, is mostly understood. How it got that way is not. Both of those things are true simultaneously, and neither one cancels the other out. If you've made it this far and something in here caught your attention, a detail, a question, an idea you want to follow further, there are other videos on this channel that might sit well with you. The one on neutron star mergers covers some related territory around how stars end. The Magnetar video goes deep into what magnetic fields do at extremes. They're long. They're meant for nights like this one. Sleep well.